All right, so here we're gonna just wrap up this section with types of solutions, and we're just gonna putting that all together of what we've covered so far. So we're gonna go over a few theorems here now, very straightforward theorems, just kind of putting into mathematical language what we've kind of been working on, the intuition of the solutions of systems here. Right now the first one being is recognizing the consistency of a linear system. Right, and it says, suppose that A is the augmented matrix of a system of linear equations with n variables. And suppose also that B is a row equivalent matrix in reduced row echelon form with R non-zero rows. Then the system of equations is inconsistent if and only if column n plus 1 of B is a pivot column. Okay, so here let's take a look at an example to see what this is telling us here. Okay, so here, right, so with this theorem, again, right, something that in working through these problems, we are familiar with now, right? When we have a system, right, and all this is saying, right, so this is a system here where it has 4 variables. Okay, for this particular one, there is 4 variables, and this particular system has, since it's augmented variables, it'll have 5 columns, right? 1 additional column for the constant, right? And the theorem there is it's a stronger connection, right? When you see that if and only if, which we'll talk more throughout the semester when we work on proofs, right? It's giving me a stronger connection. So it's more like a definition of how we define inconsistent systems in terms of reduced row echelon form, right? It's stronger than simply an if-then statement, right? If-then is not always guaranteed to work when you switch around the hypothesis and the conclusion. But this is saying by definition here, essentially, the theorem is creating the definition that if the system is inconsistent, then you'll have a pivot point in the n plus 1 column, right? In that last column. Okay, and if the other thing says is if you have a matrix in reduced row echelon form, and there's a pivot column in the last column there, then the system is inconsistent, right? And again, all is just putting into words the fact that what is happening here in that last row here in the n plus 1 column here, not necessarily always the last row, right? That would depend on the number of equations, but we come with the contradiction that 0 equals to 1, right? So that's all this theorem is telling me, right? It's just telling me that a system is inconsistent if and only if, right, the last column is a pivot column. Okay, now, furthermore, let's move on here and let's take a look at another one. Give me a second. Okay, so here, all right. So now moving on here. All right, our next theorem here. So now we look at consistent systems, right? So now we know how to spot a consistent system, or excuse me, inconsistent, by having that n plus 1 column be a pivot column. But now we're going to turn our attention to a consistent system and take a look at the letters R previously discussed in this section, and the number of variables and how those are related and what that tells us about the solution. Right, and that comes from this theorem, CSRN. So consistent systems, R and N. So how are these related, right? Suppose A is the augmented matrix of a consistent system of linear equations with n variables. And suppose also that B is a row equivalent matrix in reduced row echelon form with R pivot columns. All right, then R is less than or equal to n. Okay, and if R is equal to n, then the system has a unique solution. And if R is less than n, then the system has infinitely many solutions. Okay, all right. So here, Here we're only looking at consistent systems, so what it's telling me is that R will always be less than or equal to N for consistent systems, right? So R will never be more than N, the number of variables that we have, right? So looking at, let's bring up a couple of examples here. Okay, so here are two augmented matrix and the resulting reduced row echelon form. Okay, so in this case here we have N to be 3, right? And then here the number of pivots also is 3. Okay, so it's a consistent system, right? And in this case N is equal to 3, and as we can see, right, we have a unique solution. All right, now here is another system here in reduced row echelon form. Now here N is equal to 4, right? Remember the last column is our column of constants here. So here in this case, the number of variables is 4 for this particular system, right? And looking at this one here, this one also has 3 pivots. So R is 3, right? And now as it turns out, N minus R is 4 minus 3, which is 1. And we can see that corresponds with one free variable, that being x4 in this particular example. Okay, so you can see the connection, why it's helpful for this reduced row echelon form, because we can derive a lot of knowledge from this form of the system of equations here. Okay, so now we know how N and R are related for consistent systems. And now here, let's take a look. Free variables for consistent systems, right? And it says suppose A is the augmented matrix for a consistent system of linear equations with n variables. Hold on, forget to switch over here. Okay, so here I'm looking at theorem FVCS. So free variables for consistent systems. Suppose A is the augmented matrix of a consistent system of linear equations with n variables. Suppose also that B is a row equivalent matrix in reduced row echelon form with R rows that are not completely zeros. Then the solution set can be described with n minus R free variables. Okay, and now here, going back to the examples we just covered, we can see that this is the case, right? When they have a unique solution, then n is always going to equal to r, right? So there are n minus r will always yield a 0, so there will be no free variables, right? When that doesn't happen, right, when we get a non-zero number, right, or a positive value from n minus r, right, then in that case we have a free variable, as we do here, right? And that is going to lead us to infinite number of solutions. Okay, so now I think here to finally wrap up this section here, our last theorem states theorem PSSLS, possible solution sets for linear systems. Right? A system of linear equations has no solution, a unique solution, or infinitely many solutions, right? And here again, this comes from the previous theorem, where previous couple theorems. The first one where we talked about pivot columns. If the last column is a pivot column, it's inconsistent, so no solution. So that's that part. And then the last two focused on consistent solutions. And one of two things can happen, as we saw. If r is equal to n, we have a unique solution, so 1. If r is less than n, we have a free variable, right? And if we have a free variable can be any real number. That's the field that we are dealing with the solutions. And then that leads us to infinite number of solutions, right? So there will never be a case that you have two solutions for a linear system. If it's consistent, it's either one or infinite number of solutions.